Welcome back to Math's Playground. Today we'll be doing some stars and bars problems. They're basically permutations and combinations problems, but just a different way to solve them. So we have two basic problems and three challenge problems. First question. There are 9 identical marbles and 3 children. In how many ways can the marbles be distributed if each child may receive any number of marbles, including 0? Okay, so if we make a chart, um, there are 3 children, so C1, C2, and C3. We need 2 bars to separate all of these. So our number of bars will be 2. Our number of stars, which is basically the number of marbles, will be 9 right here. So our total objects over here will be 2 bars, and let's see, 1, 2, 3, 4, 5, 6, 7, 8, and 9 stars, which is 11 things. So now, how many ways can we place these 2 bars in all of these 11 objects? So that would be, for the first bar, there are 11 places. For the second bar, there are 10 places, divided by 2 factorial, because these 2 bars are the same things. Well, they're identical, and they can arrange themselves in 2 factorial ways. And we wouldn't be able to see it because they're both identical. So we would have 11 times 5, which is 55. Okay, we have another basic question, and then we're on to the challenge. Okay, second question. Well, second basic problem. There are 14 identical pencils and 4 students. Each student must receive at least 1 pencil. How many different distributions are possible? Okay, so let's do the number of bars first. So our number of bars will be 3, because child 1, child 2, child 3, and child 4. So 1, 2, and 3 bars. And now stars. There won't be 14 because there are 4 students and each student must receive at least 1 pencil. So we will have 14 minus, if each of the 4 students get 1 pencil, then there would be 4 pencils gone. So we would have 10 stars in total. So now total objects here will be 3 plus 10, which is 13. So now there are 3 bars. So how many ways can you place 3 bars in 13 objects? For the first bar, 13 times 12 times 11 divided by 3 factorial, because the bars can arrange in between themselves in 3 factorial ways. So 3 factorial and 12 can cross out, giving 12 a 2. So we would have 286. On to challenge problems. Okay, challenging problem number 1. There are 18 identical cookies and 5 children. Each child must receive at least 2 cookies, and the oldest child must receive at least 5 cookies. How many different distributions are possible? So we have our bars, which in this case would be 4, and then our stars. So we have 18. Well, only 4 of the children will receive at least 2, so -8 minus the older child must receive at least 5 cookies, so -5. Um, and that would be 5. So here are total objects. Total would be 4 plus 5, which is 9. So now this would be 9 times 8 times 7 times 6 divided by 4 factorial. So we end up with 126. Challenging problem number 2. Well, 1 wasn't too unfamiliar, but and it was a little familiar, but we'll see what happens next. Okay, challenging problem number 2. There are 16 identical candies and 4 children. Each child must receive at least 2 candies, and no child may receive more than 6 candies. How many different distributions are possible? Okay, so we have our bars, which would be 3. We have our stars, which would be 16 minus 4 times 2, which is equal to 8. So our total object would be 11. Okay, so it says no child may receive more than 6 candies. So what? So let's first do this problem. Let's do this problem the way we would if it hadn't had a limit, which would say no child may receive more than 6 candies. So that would be 11 times 10 times 9 divided by 3 times 2 times 1, so 2, 2. Okay, so we're left with 11 times 5 times 3, which is 165. Okay, so that would be if there hadn't been a limit. Now, we have child A, child B, child C, and child D. So each of them have 2. Now, if child A went just over the limit and got 5 more after we do all of these, after we do this, if child A just goes right above the limit and gets 5, then these 2 are greater than 6 because child A got 7. So now, so child A got 7, which is just over the limit. So now there are 3 left, right? So if there are 3 left, we can do this as a stars and bars problem over here to see how many ways we can distribute the 3 left, the 3 candies that are left, in between these 4 children. So, wait, if I go up here, so our bars would be 3. Our stars would also be 3 because there are 3 left. So our total is 6. Our total is 6. So now we have 6 times 5 times 4 divided by 3 factorial, which is equal to 20. So that would be 20 ways to distribute these 3 left and all of these guys. So now I did it with child A. Child A got the 5 extra, but it could have been child B or child C or child D. But for each of these people, whoever it is, we would have 20. So from 165, we have to subtract 20 times 4, which is 80. So 165 minus 80, we have 85. And that's your answer. So that's why it's challenging. It's not just stars and bars. There's some other stuff, but at the end of the day, it is a stars and bars problem because that's how we start off, and that's the most important part. Okay, challenging problem number 3, and our last problem. There are 20 identical apples and 5 children. Each child must receive at least 2 apples, and exactly 2 children receive the same number of apples, while the other 3 receive different numbers. How many distributions are possible? So let's start off with stars and bars. So our number of stars would be 20 minus 5 times 2, which is 10. So our total number of stars would be 10. And then our bars, we have 4 bars. Okay. So now let's just do this by listing. So we have case 1 where the repeated number is 0. So how many ways can we do this? So we have 0, 0. Now the other 3 numbers have to be different and they have to add up to 10. So our first case would be 0, 0, 1, 2, 7. The second case would be 0, 0, 2, 3, 5, 0, 0, 1, 5, 4, and 0, 0, 2, 0, 0, not 2. We would have 0, 0, 1, 6, 3. So, there aren't any more, so there are these 4 cases. So there would be 4 of these options for case 1. Now, case 2 would be where the repeated number is 1. So, we have 1, 1, and then the other 3 numbers have to be different. But this time they have to add up to 8 because we already have these 2 over here. So we have 1, 1, 0, 2, 6, and 1, 1, 0, 3, 5. Okay, now our case 3 would be where the repeated number is 2. So we have 2, 2, 0, 1, 5. Now, let's see if we can have a case 4. So case 4 would be where the repeated number is 3. So 3, 3. Now the other 3 numbers have to add up to 4 and they have to be different. So if we do 0, 1, 3 wouldn't work because it says exactly 2 children receive the same number of apples. And there's 3 threes, so that wouldn't work. We could have 3, 3, 0, 2, 2, but we have 2 twos. So that wouldn't work. So it looks like we only have 1, 2, 3, 4, 5, 6, and 7 cases. But that's not our answer because because we wrote these in a certain order. But let's pretend for a second that all of these numbers are different objects. So, and there are 5 children. So let's think in permutations way. So we have these 5 objects, and how many ways can I distribute these to 5 children? And we know that these 2 objects are the same. So that would be 5 factorial divided by 2 factorial because 2 objects are the same. And this is just for 1. So we'd have to multiply by 7 because we found 7 cases. And that would give us a total of 60 times 7, which is equal to 420 ways. That's a lot. I don't think we could have listed them and gotten it. That would have taken way long. See you next time, math experts.